My name is Wiktor Mucha. I'm a PhD student in Computer Vision Lab at TU Wien, and in this project I'm ESR number 10. And today I will talk about some research that was carried during my PhD. And I titled the presentation for today, Understanding Human Behavior with Wearable Cameras Based on Information from the Human Hand. Sorry. Okay. So let's start with a little introduction and some basic definition that will give you an overview of what am I talking today. The presentation on my research is about the wearable cameras, so the cameras that we wear on our body. You can see on the slide the person wearing the camera attached to the collar of the t-shirt. And the advantage of this is that image captured this way gives us very rich information about the environment and what is happening in the user life. And we call this egocentric perspective because this is the image that we record presents the perspective of the user wearing a camera. So here also, as I mentioned the title, I'm interested in the hand pose modeling from that perspective. So by this, I understand the task of reconstruction of 21 key points describing the hand of the user in the 2D or 3D space. So you can see the key points representing the hand also in another image. So when we talk about behavior analysis and modeling, we always have to think about the time in which we consider the monitored behavior. So we have division from the shorter time period to the longer. So we can talk about from the shortest one, so from motion to action and activity, and then finalize on the behavior. So we can have short-term or long-term monitoring. So what's the difference? In the long term, we are more focused on routine, and in the short term, we are more focused on the real time and what's happening right now. So in the longer term, here we can think about activities, what a person is doing throughout the month, what activities. But if we talk about the real time and short term, we are focused on action. So we can detail them in more, maybe provide assistance. So for example, if we would monitor some food-related scene and food-related behavior, in the longer time we can register where person tends to eat in which places. But in the shorter term, we would try to detect exactly the products, the food that are on the plate, and estimate the micro-macro ingredients. Here on this slide, you can see egocentric actions performed in the kitchen. And as you might see, the main part of the scene are the human hands, no matter the action that is performed. Yeah? So the quick observation from this animation is that, as I said, hands play a main role in the egocentric scene, alongside with the manipulated objects. So most of the actions, there are just different hand movements that are related to the certain objects. So we can think about picking up something, and I can pick up the phone or I can pick up the glass. But it's different action, but same hand movement, just a different object. Same with the rotation. We can rotate the bottle cap and open the bottle, or we can rotate the tap in the sink. Also, several activities of daily living are based on human hands, so like eating, drinking, taking medication, or reading. In general, manipulations with the objects. So that's why modeling hands here is interesting for us. So how do we estimate the hand pose in the egocentric view? So the first approach that we have tried is top-down approach. So we have a network which takes the egocentric image in the input, so the most to the left. And first what we do, we try to detect regions where the hand is. So we use for this a hand detector. And having these regions, for each region, we apply the network that is supposed to estimate hand pose. And here we use EfficientNet as a feature extraction, and then features, they are processed with the prediction head created of series of transposed convolution, which results in the heat maps that they represent the probability of the key point location in the image. But everything has pros and cons, and here the main advantage is that we have more data because we don't need egocentric data to train this. We can train it on other data sets where we have hands and the labels for that. But the disadvantage is that we need multiple forward paths through the backbone, which is the most computationally heavy. Because it has to be done for each region where we see the hand. And then also another disadvantage is that in egocentric view we have many hand-to-hand interactions or interaction of hands and objects where we have occlusions. Our hands are not even occluded but very close to each other. And because of this hand detection stage, we are segmenting these frames and dividing the hands from each other, and we are not able to train these interactions through the network. So another approach that we can do here is opposite way. It's bottom up. So we have one forward pass through the feature extraction. It's the same feature extraction, efficient net again, but from the feature map that we have from that backbone network, we have for each hand prediction head. So we have now again the pose estimation head from the transposed convolutions for each hand. And additionally, we have MLP networks which are predicting if the head appears in the image or not, so kind of the detection. The advantage here is that we have this single forward path, so it's better regarding the computation time. But also another main advantage is that we consider the full scope of interactions between hands, so we are able to perform better in this interaction scenario. The advantage is that we have less available data because we need egocentric data sets for that, and there are only a couple available right now for the public audience. So if we look at the result here in this table, it's a result of our F-hand net and network, which is based on hand detection, so the first approach. And it's tested on freehand dataset. And you can see that the results here, they are best out of any method. So the network should perform quite well also in other scenarios. But unfortunately, if we go to the egocentric view, as I said, there are occlusions and interaction between hands, and this method doesn't perform that well here. And this is where the approach created for egocentric view performs better. So we can see that F-hand EgoNet, the network when we have the heads for each hand, without the detection stage, outperforms other methods in the both dataset that we tested, egocentric dataset, so H2O dataset and FPHA dataset. Then further, if we look at the edge scenarios, so scenarios where we have two hands either interacting with each other, so overlapping or clearly separated, we would like a method which performs similarly in both conditions. So it's able to model as good when the hands are separate and as good as when they are interacting. So here again, this method F-hand EgoNet that we propose performs with the smallest error, but also with the minimal gap between these two scenarios. And on the right side, you can see that the detection-based methods like F-hand-net or post-ResNet 50 or MediaPipe, they have this gap larger between the scenarios. So that gave us the 2D pose, but what about the 3D pose? The advantage of the 3D pose is that we have one more coordinate that we are aware of, so more information regarding the depth. So if we would like to obtain this 3D information from the RGB, we can extend the presented F-hand EgoNet architecture with the MLPs for each hand, which are regressing the Z coordinate. So this we have all X, Y, Z information about each key point of the hand in the scene. So with this regression MLP networks, we have something that we call 2.5D coordinates, not really 3D. To obtain the 3D, we need to use the pinhole camera model and transform this into the camera space. So further to improve that, we proposed the SHARP architecture, which is the full name segmentation of hands and arms by range using pseudo-depth. So in egocentric view, the characteristic thing is that we have these hands, as you could see in the action, and they manipulate with object. And this is actually what interests us. We don't want more of the scene. So we have tried to segment it, but without training any additional models. So what we do here is that we take just the RGB single image input, and we use the depth estimation network, which gives us information about distance, yeah, but it's not the real information, it's just the estimation from the model. And then we segment using the range of our arms, because of course our arms, they have fixed range, so we cannot, it's a constant value, so we segment the scene using this technique, and we achieve the improvement of the 3D hand pose. So here, the first result you can see, this is error in the right side, 35 millimeters. This is without the SHARP method. And when we use SHARP, the results improve to 28 millimeters, so closer and closer to the better performance. And in the experiments, we swap this pseudo-depth information with the real depth image coming from the depth sensor. And it's kind of useless scenario because we don't want to use additional sensor, but it gives us an idea if we will have a better models, what we can get. And here we achieved the 25 millimeters, which is the overall best result in this data set. So I said about this segmentation threshold of the human arms range. So you can see on the top the scene with the different distance segmented. So this is normalized, so values from 0 to 1. And in the bottom you can see how the post-estimation error behaves with different thresholds. So on 0.47 we have this sweet spot where the performance is the best. And with the higher distance we start to lose the information that is necessary. So just basically we cut off the hands. Here are some qualitative results. So here on the left side you can see the examples where this performance is better. In the top 2D you cannot see much because the skeletons, they cover each other, overlap. But the difference is visible in the 3D, so in the bottom where the blue estimations are better than the red ones. And on the right side, a negative example where this threshold distance is too big and cuts off partially the hand, and the result decreases. All right, so we were able to estimate the hand pose, and how can we use it now? Why is it interesting? So first, for action recognition. So here we propose the network for action recognition based on the head pose information and object information. The advantage is here that we can use the pre-trained model, or we can change these hand pose networks for different models here and compare them. We can also update the object detection. If we would have a better algorithm, we can reduce the cost of learning because we can use the pre-trained networks. Also, there is some advantage regarding the privacy because as we extracting the skeletons, then we can remove the full image from the device, for example. So how does it work? First, we have the input sequence of frames representing the action. In this case, we consider 20 frames, so if the action is shorter, we have to pad it, and if it's longer, we are subsampling it. Then we use the object detection. So far, we were using YOLO V7, and from that we get the information which describes the interacted object with the points representing the corners of the bounding box from the detected object and the label of the object. So further, we use the hand pose estimation. It can be one of the networks that I have just presented, so either top-down or bottom-up. And from this, we have each frame described as a vector of points for each hand and for the object with the label. So Further, each frame is an input for a transformer encoder as a token, and transformer encoder allows us to embed the temporal features from the action. And further, these features with the MLP classifier gives us information about the action label. So for example, grab a book or place a book, pick up the milk, etc. So what we observe here is that there is a strong correlation between the action and the hand pose estimation method. So how accurate is it? And on the top plot figure, you can see the action recognition with different hand pose methods, from the left, from the best hand pose, to the right, to the worst. And in this scenario, we train the action recognition with the ground truth skeletons that we have in the data set, and further we evaluate it with different hand pose estimation methods. And then we see the same observation in the bottom, but in that case we train also with different methods for hand pose estimation. So regarding the results, this approach achieves the best results in H2O dataset, 91.3 action recognition accuracy, and very competitive results in FPHA with 94.4. And if we talk about the inference time here, the main advantage of using 2D is that we have less complicated, less complex network, because we are not regressing this 3D information. So that's when we use the first model named FHandigonet. So what we do is that we test the inference with 1000 runs on NVIDIA RTX 3060 GPU, and we get the mean times of inference. So here you can see on the figure the circles, they symbolize the size and number of trainable parameters. So our method on green in the top left corner is the fastest with the highest action recognition, and with the medium amount of trainable parameters. If we would swap in this action recognition network for the This what?
No, the other one. Yeah, the other one is recording. Yeah, but
yes, oh, sorry. Yes, so if we would change the hand pose information in the same network for the hand pose estimation from Sharp and with the 3D information, we would result even in a better improvement of the action recognition to 91.7. So if we would talk about the inference time, here again the Sharp places us in the middle, but still being faster than the second best method. So another way when we use the hand pose, the struggle determination, so we have input video representing the action, and we try to detect if the user struggles or not, or estimate the level in the four-way regarding the struggle. So here, using the semantic features and temporal features from the video, but also merging this with the hand pose information, we are able to achieve the best result overall of 89% in the binary task. Another thing that I'm working on now, and where I plan to use the hand pose estimation, is the hand rehabilitation. So the motivation here is that stroke remains the third leading cause of the mortality and disability, and majority of patients, they require hand rehabilitation, so another medical personnel that will help them get back to the shape. On the top you can see some examples of these exercises. This is very preliminary stage, but here we have different challenges like exercise recognition or repetition counting, detection where the exercise starts or finish, and the evaluation of the exercise. So for this stage I have recordings from 9 users in age between 25 to 88 years old, performing 3 common recommended exercises for stroke patients for hand rehabilitation. For each hand it gives me in total 25 exercises. And so far in validation I'm still not the test stage, but I was able to achieve 97% with the slow fast network. And this brings me to the conclusion, so I just will say here some findings that that I presented. So what we observed is that the bottom-up methods then tend to fail in the egocentric perspective for hand pose estimation. So if we want to precisely achieve the interactions between hands, we have to skip the detection phase. In certain scenarios, if we would like to reduce the inference, the 2D pose information is a promising alternative to the 3D pose. So for example, if you want to work in real time on smart glasses or some devices like that, then we can consider this scenario. And also using pseudo-death information to remove the irrelevant scene parts improves the hand pose estimation. And finally, what is important to remember is that accurate pose description is essential for correct action understanding, but also tasks like struggle determination and probably many other tasks that are yet to be researched in the egocentric image processing. Thank you.
Thank you, Wiktor. Any question here? No? I have, no? Yes? No? Okay. I have some. The first one is, you have shown a graph of the results of your network with overlapping or separated.
Yes.
So the input to that network is the whole image, it's not the area where the hands are. It's not a bounding box of the hand. It's the whole.
Yes, it's a whole image. So, for a case where we need the hand detection, we have full image. We detect the regions. We perform the hand pose for these regions, and then we broadcast this to the full frame. Yeah. And for other network, we just input the full image and we get the result.
So you have shown the results for overlapping hands, separated hands. Would the results change about recognizing if the right hand or the left hand are there, if only one hand is in the image? So you have shown overlapping, separated,
yes.
But not only one hand.
Not only one hand. Yes, that's true. This would give, I think, similar information, but it's less interesting. Yes, because the main challenge is this overlapping scenario here, or interaction with the objects. Yeah?
Yeah, but the thing is that when you have the two hands,
yes,
the system can learn that the hand that is in this side is the right hand, the hand that is in this side is the left hand. If there is only one of them, then you don't have that information that you have the two hands there.
Yes, that's true, but during the training there are augmentations of the image and also the scenes with single hand.
Okay, it would be good to see.
So
it would be good to see the same graph with the three possibilities.
That's true. That would be interesting to edit. Yes, the idea was to show the better performance in this interaction scene. So the pose estimation just for a single hand is not that challenging. So we found it less interesting to present.
But in your dataset, you have images with only one hand appearing.
Also, yes. Yes, of course, because sometimes some objects you manipulate with just one hand, some other with two, like opening the bottle. Yeah, you need two hands, for example.
And another question is, in these datasets, when you talk about egocentric vision, the camera is on the head or on the torso?
So on one data set, the camera is on the head, and on the other data set, the camera is, I think, also on the head, but it's older data set, older camera, and gives very different, the very different image regarding the angle that you can see and the quality. So it's a bit different scene. To be honest, if you would take a GoPro camera, looks more like, or another with wide angle looks more like recorded from the chest, but I think it's from the scene.
No, it's because when the camera is worn on the head, there is much more motion of the camera than if the camera is on the torso.
Yes, that's true. But also from the torso, the hands are very visible. They are in the center of the scene, but the human, like the hands and the palms, they are not that usually visible because the main part are the forearms here. So for this, I think it makes more sense to have the camera on the head.
Okay. Any other question? Any question there? No? Okay. So thank you, Wiktor.
Thank you.